Indigent specializes in developing software for digitalized innovation process. These softwares seamlessly integrate property prediction models based on AI, scientific AI, and material sci as process scale-up models. As researchers design new products and formulation, they get real-time feedback from I-Rheo. This allows researchers to focus on the end goal of reducing developmental times and costs and be successful at the very first industrial trial. As we know, industrial-scale trials are expensive and hard to come by. They can also use these tools to improve the quality of innovation and find new white spaces. Even though Inogen is a relatively young company, two of our software, I-Rheo and Inogen Pi, are already being commercially used. I-Rheo can be used to simulate various industrial processes using thermoset polymer systems. These processes include filament winding, pultrusion, coatings, and adhesives, and many others. All the necessary tools to simulate these processes are seamlessly integrated. In filament winding and other relatively slow processes, such as coatings and adhesives, time temperature profile of resin system is known with certainty. These processes can be simulated using the given time temperature profile page. In filament winding, key factors to watch are the initial resin viscosity and the minimum resin viscosity during the process. The initial viscosity dictates the winding pressure and the resin content, while the minimum viscosity dictates the quality of wetting and resin squeezing out. With I-Rheo, simulation is very simple and straightforward. Users do not have to know any math modeling. First, on the Choose Formulations pages, selection up to 5 resin systems. Next, go to the given time temperature profile page and enter the time temperature profile. As we enter the time temperature profile, I-Rheo updates the simulation results for the selected resin systems. The key factors to watch are the degree of cure, the initial resin viscosity, the minimum viscosity during the heating cycle, as well as the gel time. If the minimum viscosity is too high, fibers may not wet properly, and if it is too low, resin may squeeze out of the fibers. If the glass transition temperature is higher than the material temperature, material vitrifies and reactions stop. In case of pultrusion, the key factors to watch are pot life, initial viscosity, minimum material viscosity, the distance into the dye where the resin gels, the distance into the dye where the material attained the maximum value, and the final degree cure. However, we only know the dye temperature profile. We do not know the material temperature as it moves through the dye. We must simultaneously solve the heat transfer, reaction kinetics, and rheology equations. While many methods have been used to solve these equations, the finite control volume is preferred. Inogen's proprietary algorithms are fast and powerful. Moreover, researchers do not need any background in finite elements or finite control volumes. With I-Rheo, pultrusion simulation is very simple and straightforward. First, on the Choose Formulations pages, selection up to 5 resin systems. Next, go to the pultrusion page and specify the material properties, such as thermal conductivity and specific heat. These values can also be chosen from the database. Choose the shape of the part from the list of available shapes. More shapes can be added if needed. Specify dye length, line speed, dye length, and dimension of the dye and the part. Specify position of material element on the cross-section of the part. I-Rheo will display results for this element. You can also change the material element later on. Specify the dye temperature profile. You may add more heating elements or delete an existing system, if needed. Now that all the necessary data has been entered, press the Run Pultrusion Simulation button. I-Rheo will solve the control volume equations for each resin system. Resins Pull 1, 3, and 4 have the similar curing profile. Pull 2 is showing a slower curing profile. Other factors to watch are the initial viscosity, the minimum viscosity, and the distance into the dye where the material gels. Glass transition temperature and the material temperature as the material elements move through the dye are key factors as well. The maximum temperature in the middle element of the part must take place before it exits the dye. Otherwise, the surface may crack due to thermal stresses. The process simulation models take their information about reaction kinetics and viscosity from rheokinetic models. The rheokinetic models are unique to the resin system and must be developed for every new resin system. Once developed, they can be saved to the database for use in industrial process simulations. I-Rheo makes it simple and straightforward for researchers to develop these models. They do not need to have any background in math modeling. First step in developing a kinetic model is to read DSC scan files. As I-Rheo reads the file, it detects the reaction peaks, draws the baseline, and calculates the degree of cure as a function of time and temperature. I-Rheo needs at least 2 DSC dynamic scans or 3 isothermal scans. It allows to name each scan file. A combination dynamic and isothermal scans can be used well. I-Rheo also calculates the heat of reaction, which is needed in process simulations. A correct value of the sample mass is needed for these calculations. Even though I-Rheo does a good job in identifying the beginning and the end of the reaction peaks, users can change these points if needed. Just press the starting time or the end time button and right-click at the desired point. Once all the data is uploaded, go to the kinetic model page and select the type of kinetic model to be used. Finally, train the model for the given resin system. Intelligent model with vitrification is a proprietary model. It takes into account the effect of vitrification on reaction kinetics. A kinetic model is a prerequisite for the rheology model. The first step in developing a rheology model is to read rheology scan data. As I-Rheo reads the data file, it identifies the data range that will be used for optimization. Users can override these limits to exclude erroneous data. Just press the starting time or the end time button and right-click at the desired point. As in case of kinetic model, user can specify a name each scan dataset / I-Rheo needs data from at least one temperature scan or one isophyll scan when intelligent rheology model is used. Additional data is needed to use other type of models. Once all the rheology data is uploaded, go to the rheology model page and choose the type of rheology model to be used. Finally, optimize the rheology model to improve predictions for the given resin system. After developing the real kinetic models, the models must be saved to the database before they can be used for process simulations. Go to the props and database page and enter the name of the resin system. This name will be later on used to identify the resin system when selecting resins for process simulations. I-Rheo also allows the users to save key mechanical properties of the resin system. More mechanical properties can be added to the list if needed. Finally, upload the model to the database by pressing the Upload/Update Model and Material Properties button. I-Rheo will update the model ID number and the time it was updated last. I-Rheo's algorithms are robust and fast. It allows users to simulate real-life industrial scale processes without having any background in finite element analysis and math modeling. I-Rheo can also be used standalone or as part of digital innovation process software. Intelligent Pi provides real-time feedback from our proprietary scientific AI models as researchers design new resin systems and applications. For questions, please contact at convenience. Our scientists can customize these software to your specific needs.